Hi, my name is Dustin Wilson, and today I'd like to walk you through this project I've been working on over the last couple weeks. So what I wanted to do was re-implement some of the basic papers in the study of computer vision in PyTorch, and then use that re-implementation to train a model on a DL1 instance. The models that I chose to replicate were Alec Radford's DCGAN paper. DCGAN is the predecessor to a lot of the generative models that we see today and in the last 6 years or so. And it's easy to implement, fast to train, and more intuitive than its successors, but it does have a couple problems. It works on small images only, even though we were able to scale that up using some additional convolutional layers. And it's relatively unstable compared to some other methods, which I was also able to address in the last month or so. The dataset that I used for this project was the Mapillary Street Level Sequences dataset, which consists of 1.6 million images from 30 major cities all over the world. The generated images, ideally, can have a lot of applications in self-driving cars and sort of general recognition tasks, and be used as an input to other generative models or segmentation or classification models. So the architecture that we used for this, the AWS infrastructure, was centered around a single training instance, but also had some auxiliary instances for monitoring that instance, chiefly Grafana instance, which was hooked up to CloudWatch, and running TensorBoard to keep track of the loss and intermediate training metrics as well. So I wanted to make sure that before even we moved to DL1, performance was solid. And that meant that we were training off of a fast disk, optimizing batch size, using distributed backends, mixed precision, and then critically, we were using a different optimizer than suggested in the original DCGAN paper, AtomW, because one, that gives us more stability because we're doing the weight decay, and two, because when we move over to the Habana instance, we can use fused AtomW, which gives us the weight decay and also multiple ops on the Synapse API. So once we moved over to the Habana instance, we got pretty good performance without too much of the sort of grinding performance tuning that we were doing on the GPU instances. It just translated really well, I found. Aside from, we made some changes for, HCCL rather than NCCL, HMP versus AMP, and then we trained off of local storage rather than EBS once we were on the DL1. We had access to those, I think, 4 terabytes of local storage. So let's do a quick demo. So I've put up this site, gan.dmw2151.com, which contains a gallery of some sample images. So as you can see, they are not quite the prettiest, but they are sort of in line with what we would expect for DCGAN. In retrospect, we could have perhaps used a more modern architecture, but I thought that sort of the low-level control that I got over the model with DCGAN was really important. This website also contains sort of a longer blog post explaining some of the performance implications of my choices and some more additional detail on the Mapillary dataset. Thanks for listening.